Chapter 2, Difference between ASTROS and NASTRAN in Structural Finite Element Model. Unlike NASTRAN, MPC, RBAR, RBE2, RBE3 support protocols of ASTROS have a set ID, where NASTRAN doesn't have a set ID for those cars. And set ID are required in this ASTROS protocols and are referred to by the boundary solution control command. ASTROS can optimize the structure simultaneously for multiple boundary conditions. Several types of elements are available in NASTRAN and are absent in ASTROS. For example, C-beam, C-bush, C-panda. The element stiffness and mass matrix of those elements can be exported from NASTRAN and imported into ASTROS via the K2GG, M2GG in the boundary solution control command. And in order to export those elementary matrices from NASTRAN requires keeping all the grid but only those missing elements in the NASTRAN input file. Then you can output the KGGM and the GZ mass and stiffness matrix of those missing elements from the NASTRAN and import it into ASTROS. And we will show you an example how to do that. And we also provide a function code called DMIG.EXE that can convert output 4 matrices from NASTRAN into DMIG input card of ASTROS. So this example shows the difference between ASTROS and NASTRAN in MPC and support. In NASTRAN, for the rigid element like RBAR or RBE2 and the support card, they do not have a set ID. So to run NASTRAN, each NASTRAN job only can perform analysis for one type of boundary condition. But for ASTROS, because RBAR, RBE3 and support, they have a set ID. So for in the boundary command, you use MPC to refer to the rigid element, and you can use the support to refer to a support card. So the MPC, RBAR, RBE2, RBE3 support protocols of ASTROS have set ID, which are referred to by different boundary conditions. ASTROS can optimize the structure simultaneously for multiple boundary conditions. Typical example for multiple boundary conditions: if you have half-span model, you can perform symmetric, you can specify symmetric, anti-symmetric boundary conditions, and then you can ASTROS can optimize the structure to satisfy the symmetric the constraints of symmetric boundary condition and anti-symmetric boundary conditions. Or you want to optimize a wing structure and to satisfy, for example, satisfy the flutter constraint of a clean wing and a wing with the underwing store. And how do you do that? For example, if you model the underwing store with a concentrated mass, then you attach the mass to a grid point. Then you connect that grid point to the wing structure using a rigid element like RBAR. Okay, so you can create a boundary. You refer to the RBAR, and then this structure will have a underwing store mass attached to the wing. Then you can specify another boundary condition where you do not refer to the RBAR, and also you SPC that grid point where the store mass is attached. You refer to different SPC ID. So therefore you have a clean wing structure. So in so doing, you can design a wing structure which satisfies for example, the flutter constraint of clean wing and also wing with underwing stores. And how to handle the missing NASTRAN elements for ASTROS? So for example, SO does not have a C beam, C bush, and C panda. So how do you handle those missing elements? So this is a typical NASTRAN input. You keep all the grid point, and but for the element you only keep those missing element of SOs like C panda and so on. Then you use this alter statement to output the KGG and MGG matrices in the output 4 format into the file name called kgg.dat mgg.dat. Okay, then you run. So you have a start.fo6 as output file of NASTRAN. You have kgg.dat and mg.dat from the assign output 4 command of NASTRAN. Then you run DMIG.EXE, and the DMIG.EXE will convert the output 4 matrices into SOS DMIG card. Then you have one DMIG card for the stiffness matrix and the mass matrix of those missing elements. And then in the boundary, you can use K2GG refer to the name of the DMIG card, and M2GG to refer to the name of the DMIG card of the mass matrix. In so doing, you can include the stiffness and the mass matrix of those missing element into SO's stiffness and global stiffness and mass matrix. And how to run DMIG.EXE? And you just type DMIG, and DMIG.EXE can be found in the folder of the miscellaneous folder in the root folder of SOs. So you type DMIG, and then DMIG.EXE will ask you several questions. The first, it will ask you what's the output file name of NASTRAN, and then you say the matrix you want in A set or G set. Then you say no. That means it's in G set. Then you want you to input the KGG MGG output 4 matrix file name, and so this time we will say K2G.dat. So this K2G.dat is the file name output by NASTRAN via the assign output 4 equals command, and then input the format of the output 4 matrix. You say 1 because it's F16.9. Input a matrix name of the DMIG card because DMIG card will require a name of the matrix. So I call it KGG.EXE into a file name to output the DMIG card. I call it KGG.DMIG. It's output the DMIG card in NASTRAN or SOS format. And I said no, so it's in SOS format. Input 1 characters either from A to Z or 1 to 9. This character is used for constructing the continuation of the DMIG input card as a Z. Okay, so the first time you have to run this DMIG.EXE twice. The first one you import the K2GG.dat, and then I call the matrix name K2GG.EXE. The next time I call mgg.dat, and I call mgg.EXE for the DMIG card, and then you insert those two cards into your SOS input file. So this is the stiffness matrix, this is the mass matrix of those missing elements, and then use K2GG, M2GG to refer to those two matrices. So you also can then, in so doing, also can include the stiffness and mass matrix of those missing elements in the SOS model. And there's some other difference between SOS and NASTRAN in modeling, in finite element modeling. The default of entry LOPT in the PCOM 1, PCOM 2 Bogota car of ASTROS is mean, where for NASTRAN is all. LOPT equals mean exclude the bending stiffness from C-craft for C-3 elements, so only include the membrane stiffness. For sizing optimization, including bending stiffness leads to a nonlinear stiffness sensitivity with respect to the thickness and may introduce conversion problem of the optimization. So if you can set up such a model where the C-craft4 and C-3 property cars only has the membrane stiffness matrix, then the stiffness and the mass matrix is linearly with respect to the thickness of the those elements. So for optimization, the problem become linear. So for the it's easier for the optimizer to find a converged solution. Also, the Lentil solver in ASTROS is activated by the EIGER car with the entry method equal to Lentils, whereas NASTRAN they use EIGER L. ASTROS does not have a C-beam element. In addition, the property car for C-bar element for specifying the cross section of beam is called P-bar1, whereas NASTRAN is called P-bar-L. The P-bar1 car of ASTROS does not include all types of cross section that NASTRAN has. NASTRAN can convert the cross section into EI and GGA and output them in terms of P-bar cards, and that can be used by ASTROS. A new property card called PBARST is developed in ASTROS to model the composite stiffener. PBARST is not available in NASTRAN. PBARST is referred to by the C-bar card, C-bar element, just like P-bar. The PBARST card allows the modeling of the shape of the composite stiffener, whose composite layout of the flange and web is specified by the PCOM card. So this is the PCOM card of NASTRAN, and the LAN, the default is include both bending and membrane stiffness in the stiffness matrix. And if you specify MEM, then you only include the membrane stiffness. If you say SYN, the plies on one side of the element are specified. So you only, because the composite layout is symmetric, you only need to specify have one side of the element with respect to the center line. But for ASTROS, LOPT, if blank, the default is mean. So you only consider the membrane stiffness. If it's all, then you consider both bending and membrane stiffness. The SYN is not supported by ASTROS, so you have to input the complete layout in the PCOM card. And for the rigid element R bar, RB2, RB3, NASTRAN does not have a set ID, whereas ASTROS has a set ID. Then you can use a boundary NPC equal to I to refer to those set ID. And we also have a NASTRAN-to-ASTROS converter. You can run this code, and this code will convert the NASTRAN input cards to ASTROS. For example, if you have a 150 C-beam element, if you run this code, it will convert C-beam into C-bar, and then so at the beginning you have 110 C-bar element, 1010 C-bar elements, 150 C-beam element. Then ASTROS to NASTRAN-to-ASTROS converter will combine the C-beam into the C-bar element. So you have 1,160 C-bar elements. And in this slide, we want to compare the ASTROS and NASTRAN input cards. If any card marked in red, that means this Bogota card input are slightly different from those in NASTRAN. If it is in green, and those Bogota card are identical to those in NASTRAN. For example, we have set 1, set 2, they are identical to NASTRAN, and those count are identical. So apply static loads, they are identical to NASTRAN. The boundary condition constraint, you have A set 1, and NPC, they are identical to NASTRAN. The P bar 1, P bar 2, P bar 3. No, R bar, RB2, RB 1, RB 2, RB 3, and R rod, that's slightly different from NASTRAN. Anything is black is totally different from NASTRAN. And we have the design variable and the optimization parameters. And all the geometry, the coordinate card, grid card, and they are all identical to NASTRAN. Material card are identical to NASTRAN. And we have DMI and DMIG card. They are slightly different from NASTRAN. And this selection list, those cards are totally different from NASTRAN. And we have a aerodynamic model, and for the structural element, the C bar and those elements are identical to NASTRAN. For the element property card and the P bar, PCOM1, PCOM2, they are identical to NASTRAN. And the P bar 1 is different from NASTRAN, and NASTRAN is called P bar L. And we have a card called PBARST, which is a new property card of ASTROS, and NASTRAN does not have this card. And this is aerodynamic data generation, and the discipline dependent problem control, and the PBARST card is used to model composite stiffeners in ASTROS, and this card is not available in NASTRAN. PBARST is referred to by C bar element, just like a P bar property card. No need to physically model the web and flange of stiffener by C4 and C3. And because if you want to impose the buckling or crippling constraint of the flange and web of a stiffener, if you use NASTRAN, you have to physically model the flange and the web of a stiffener by plate elements. That will drastically increase the size of the structural problem. So, but if you use PBARST, you can greatly simplify the complexity of the structural finite model. And in the PBARST, you can specify select a shape of the stiffener. Each web and flange refer to a PCOM card to define its composite laminate. Each web and flange can be subjected to crippling constraint by the decon crip card using analytical buckling equations of one edge-free and no edge-free simply supported plate. And the whole stiffener can be subjected to the column buckling constraint by the decon BKE. And you also can impose inter-river buckling constraint. Each layer in the PCOM card can be selected as a design variable or linked to other layer as a global design variable. Shape function can be applied to the thickness distribution of each layer along the stiffener. The smoothness of the thickness distribution of each layer along the stiffener can be ensured. So this is typical. This is the input card of PBARST, and you have PID, which is referred to by the C bar card. You can select a shape, and you can specify the non-structural mass. And A, F, E, F, rho F are the area, Young's modulus, and density between the filler between the right here and right there. After that, you have a D1, which you specify the length D1. You specify the length of the web and D2 specify the length of the flange, and another flange. Okay,